A very warm good evening to one and all. Today we have gathered here as part of the webinar series of IEEE SB SNGCE. Let's begin with a prayer. हृदयरागतन्त्रे मीट्टी स्नेहगीतमेगी कर्मभूमि तळिरिडुं വർണ്ണമേകിയും നമ്മിൽ വാഴും ആദിനാമം ഇന്നു വാഴ്ത്തിടാം ഹൃദയരാഗതന്ത്രി മീട്ടി. First, I take this opportunity to welcome the gathering. First of all, I would like to welcome our chief guest of the day, Dr. Deepak Mishra, Professor and HOD, Department of Avionics, Indian Institute of Space Science and Technology. I welcome you, sir, to this function.
Thank you, Grishma.
Next, let me welcome Professor Pratibha Verghese, Branch Counselor, IEEE SB SNGCE. I proudly welcome all the executive members and all IEEE members of IEEE SB SNGCE for today's session. Today, our session is handled by Dr. Deepak Mishra. Today, our session is handled by Dr. Deepak Mishra. He is a professor and HOD, Department of Avionics, Indian Institute of Space Science and Technology, Thiruvananthapuram. His current research focuses on developing deep learning based algorithms for computer vision applications and new architecture for deep learning. He had taught virtual reality, computer vision, and machine learning courses. Some of his research work involves virtual reality application for disaster simulation and walkthrough. He is a recipient of the prestigious SSI Young Scientist Award in the year 2012. Many of his graduate and postgraduate students have won INAE Best Project Award. His group, consisting of 16 research scholars, UG, PG, and PhD level, are actively working. His research work has resulted in 2 book chapters and around 70 plus publications in peer-reviewed journals and conferences. While his recent work with his students on developing an application for COVID AR Challenge 2020 was listed in top 15 among 300 plus participants. So, our session is based on the topic Introduction to Computer Vision. I hand over the session to Deepak sir. Sir, please.
Yeah, thank you very much, Grishma, and thank you, Dr. Pratibha, for your kind invitation. I will be sharing my screen. Please let me know if you are able to see the screen. And just to save the bandwidth, I will switch off the camera. Do you see my screen?
Yes, sir.
Okay, good. You are seeing the slides also?
Yes, sir, it's visible.
Okay, good. So, good evening, everybody. And I'm really honored to be part of this lecture series. I will be talking very basics about the computer vision. I generally teach this full one semester course here in IIST to our both undergraduate and postgraduate student. So these are the slides which I have made for my student, and some of the slides I have taken from different places. So just to motivate you all to work in computer vision. So these are my contact address. If you have any questions now, you can ask me, or if you have any questions later, you can always approach me, and I will be very happy to help you with those answers. So before we go into the basic computer vision, I like all of you to know that what are the prerequisites for doing some work in the computer vision. First of all, you should have some basic computer science skill. Like you should know what is data structure, how to write simple algorithm, searching, sorting, all basic, very basic data structure you should know. You should also understand the basics of Python We should be able to have no fear of programming in Python. We should also the little bit advanced library like TensorFlow, PyTorch, MATLAB, etc. And then also you should have an interest in programming, because most of the time computer vision deals with the programming aspect, although hardware is also part of it. But in general, we need to deal with the software aspect of the vision. So that is where programming is one such thing you should have interest into. And then moreover, you need also some math skill, let's say calculus, linear algebra, probability, and information theory. So you are already undergoing a lot of courses in maths. I hope that would make you very sufficiently knowledgeable to pursue research in the computer vision area. So just to before I begin, I want to acknowledgement a lot of research material or teaching material available in the internet. In particular, the Stephen Steeds and Forseth, Mubarak Shah, Jitendra Malik, and many other people who have made their slides available, which I can actually use it for learning and teaching purposes. So, what are the goal of a computer vision? So, if you see, vision is basically everywhere, because most of the time we have seen that our human eyes are capturing a lot of information from surroundings, and we do a lot of interpretation. Let's say now you are listening to this lecture, so you are using your eyes to see the slides and trying to understand what is there available in the slides, and then comprehend, and then try to reason about it, and then create something kind of a knowledge from the images. So it's not only image processing, but you want to really pull out some of kind of a geometric or semantic information from the scene. And if you see a very cartoonish scene here, you see a light source. Let's say sun is the light source. Then there is a person sitting there on a desk. Then this light basically hits onto the different surfaces, and due to the properties of the or due to the different properties of the different objects available in the scene, the light would be reflecting in a different directions. And you see that there are a lot of interaction of the lights are happening, or the rays are happening on the object. And then these light of interaction, this interaction actually help us to really capture into a camera. So our idea of the goal of the computer vision is to convert light into a meaning. So it's just not only we are capturing the light information, but also trying to extract the meaning out of this lights. That is what basically the idea of a computer vision. And there is an acquisition part of the computer vision where we take the images, we record the mobile. Let's say you can use the mobile camera to capture some images or video, or you can use very hi-fi camera like DSLR camera or movie camera or any other camera basically to record multiple such data, and then you process it to basically extract the meaning from the images. So what is computer vision? So this is a very interesting pipeline. You can see that thing which is a, so in general is valid for all possible cases. So you give an input as an image. This is one image, and then this could be a real world object, or it could be a image itself, and you use this sensing device to capture the world object. World, what I mean when I say world means the in and around surrounding. We capture something from the camera. So you are capturing the information or the light information from the surrounding using a camera, that is called the sensing device. This sensing device, whatever is captured, converts this analog information to digital information, and then transfer or store into a memory. And then this program or computer which is lying in the PC would actually try to extract the knowledge from this data which is stored into the memory, and then it will try to tell that, okay, let's say in this particular case it will telling that, okay, there is a banana, there is an orange, there are lemons, there are peaches, how many such banana, okay, how many such are there, that kind of a answer we are giving from a image or computer vision processing. So earlier what happened, if you see that early time, whenever let's say 2010 and before, people used to work in a classical computer vision most of the time. So classical computer vision means you acquire the images, do certain image processing task, extract the feature. When I say feature means Here in this particular case, you can see color is the feature, shape is the one of the feature, texture could be one of the feature. It could be the shape of the object. It could be any such thing which can distinguish from one object to other object. That is what we call as a feature. So once you extract the feature, then you give these features to a classifier, and this classifier would be classifying into particular category. Let's say we can learn this classifier. It could be mostly machine learning algorithm, which is taking this image feature and then putting into some category like apple, orange, banana, lemon, and so on and so forth. That is called the classical computer vision pipeline. And nowadays, what we have is basically a modern computer vision pipeline. In the modern computer vision pipeline, what we have a images which is we are acquiring from the sensors, and then we have a deep neural network architecture. So it's kind of a trending, it's kind of an end-to-end trainable neural network architecture. I hope all of you are aware of the neural network. If not, it is some kind of a algorithm which takes in data and then you can train for generating the feature, as well as you can do a machine learning task of classification. And moreover, many times you can some of the image processing tasks also we can do while training a deep neural network. So deep neural network model basically captures all possible aspects of a classical computer vision by having a single network which is end-to-end trainable, and then we can generate the desired output, which is as the same as the previous aspect. So that is the basic difference between the classical and modern computer vision. And mostly deep neural networks are being taught in the most of the colleges. The idea here is to use the neural network to extract the information from the data, and that is the typical pipeline. So this is what people do, and I will not discuss any deep neural network architecture here, but there are many architectures available like VGGNet, LXNet, GoogleNet, and SiamesNet. There are many other ResNet, DenseNet. Several. There is a whole family of neural networks are possible that one can use to extract the features and then do a classification. So if you go to literature, you will say that ImageNet is the one such big data set which has been used to train the deep neural network model for image classification task. So you see this particular image, and if you see this particular image, okay. So I just to caution all the students, if you have any question, any comments or any clarification, you please interrupt me. I will be very happy to answer as and when you have any question. So so here you see a very beautiful scenic picture. So our idea is to recover useful properties about the world from the images and the video. So we just see this image and then try to interpret, okay, what is this scene? It is a scene having a lot of forest area, it's a beautiful lake is there, and then it is kind of a some flag is also there, and then what kind of trees are possible, how much area is covered by water, how much is the sky area, and how much is the tree area, and can we do some more interpretation of the this video of this particular image. We can also talk about some kind of a very complicated scenario. Let's say if you see this particular thing, it is look like a traffic scenario in a very populated place, and then people are trying to come out of a particular direction, and then it's just like a jam-packed thing, and nothing is moving. Similarly, you see a scene from an Indian context. Lot of vehicles are going in one direction, and their traffic is getting meeting at this point, and then there are a lot of people standing here. There are a lot of cars are parked here. So can we count how many number of cars are there? How many people are there? Can we remove the shadow? So we see the shadow is also there. So in general, algorithm would fail to detect the shadow, and we will count also shadow as the one of the object, because we use the 3D aspect in the two-dimensional images. And here you see that a lot of birds are there. Can you count the number of birds and what they are doing, kind of behavior understanding, and so many other aspects one can see. So these are some typical practical real world problems where we in generally fail to analyze using computers. Although humans can do all the interpretation, but it is very difficult to process this information by a computer. So computer vision is a hard thing because it requires a lot of intuitions, a lot of knowledge about the practical scenario that you are working with, and then it is still affected by a lot of challenges. I will talk about a lot of challenges that are possible, and you also know that our human species, actually human species or any such species, has evolved to this extent due to the presence of visual information. Because if you see predator and prey model, the prey would be always trying to basically run away from the predator, and predator will always try to find out where is the prey so that it can feed itself. So if none of us have eyes, then we might be not able to evolve in such a strong species, because then we will have no fear and we don't know who is going to eat us, and then it will be a very difficult scenario. So this, due to the information, visual information processing capacity of all the species, we are actually seeing a very developed society at large. So in a biological aspect, you can also understand that visual cortex occupies about 50% of the macaque brain, and even in like humans are very close to this monkeys kind of a uh, development. So we also use a lot of visual information, and most of the time our visual cortex is being used for processing a lot of information in every possible millisecond. So we see, whenever we see something, we process the information. So our human brain is actually using a lot more capacity of the entire brain, and then it is basically a lot of interpretation and inference we do. But it is very hard, and if you see that, because there are people, if you see this particular picture, the question is, can we identify what kind of animals are there? So if you see that this kind of some yak kind of a thing or bull kind of a thing is there, here you can see some kind of elephant is there, but you have to give a lot of attention. Okay, you have to really look for, because this is very cluttery environment, and then you don't really see a perfect shape, and then a lot of occlusion is possible, and you might have never seen such a bull with a red color. Okay, and similarly elephant will not be at such kind of a color. So the computer vision algorithm may not know all these details which humans are evolved or learned over time, and that is what again it makes very difficult to process in general. And again, this is a very interesting example. I would like any one of you to guess this. What animal do you think it is? Do you think any animal it is?
A horse.
Horse. Okay, so although there is no sign of the horse, but actually we are saying it to be horse. So our human brain is computationally very effective, and then we even imagine something which is not there. Okay, so that's kind of a thing, and so we are very good at even working with the partial information, and then actual algorithms are not really capable of handling such information. So if you give a computer algorithm, tell what this particular scene is, they will unable to tell. Okay, that is unable to tell. So how does it all started? Actually, computer vision in general may be very old, but formally in MIT, Professor Minsky actually invited one student, summer internship student, like most of you also going for summer intern, and this boy, Mr. Gerald J. Sussman, was the undergraduate student in summer project at MIT, and that is his task was to interface camera with the computer, and that is all where, and it has all happened in 1966. So this is the report people cite in the most of the lectures, and this is how in 1966, so almost so many years, 60 plus years are over, still we are working in the computer vision area. So it's still a lot of our problems are unsolved, and still we need to go long way in this particular direction. And again, if you see this particular image, this is a very good painting. You can see here, and if you really see this, we have a lot of color information, shape information. But when the computers see only the numbers. They don't have much information about what this color is, whether it's RGB or what kind of a gray level. They only have this number, and then to interpret a number into a boat or into a particular flag is kind of a very difficult problem for a computer to solve. But although we need very fancy algorithm, we need to come up with some kind of intuitive idea how to convert this pixel information into a particular reason. So that is what actually it's become much more harder when it comes to the real application. And when I say these numbers, actually here the gray level. So in general, we store our images using 8-bit information. So 0 to 55 is the number we represent into gray level, 0 correspond to black color, 255 correspond to white color, and then in between there are several other colors are possible. And if you have multiple such, let's say 3 layer of this gray scale, it becomes the color image. So images are very highly complex function of the several variable. If you see this particular image, it's not only function of the object, but it is function of the camera parameter, the lighting conditions, and the view angle, how we take the images, even the person, what he wearing the object, what kind of a reflections are happening from the body, the absorption of the light from the different materials. There are very complex. So image is a very complex function of multiple such variable, and we need to use that complex functions and then use that images to really interpret from the those data. So you can in general say that images are very highly complex function of several variables. Here variable means the shape, color, the lighting conditions, the weather conditions, even the cloth what person is wearing, even the camera what you are wearing, taking pictures, the direction from where you take the image. If you take from an aerial view, if you from a side view, different views are possible. Again, this is another image. If you take this image taken in the Earth and this is taken in the space, you see completely different. Okay? So we don't know, whether it is actually space image. So how do you really interpret such data? It becomes a very challenging. And you see that this is a very shiny surface. You see the reflection of the person which is in front of the person. So again, it becomes very much complicated how this light interact with each other, and then you can interpret such data. This is just to tell you that okay, if you see this particular image, it looks like a 3D Lego army, and it is drawn in a very very fancy way. Like you can see from this view, you see that it's a some ground has been dug, and then these people are standing below the earth surface. And if you see from a different view angle, and this is the actual different view, you can see that now the same image would completely look like a planar. Okay, there is no such 3D you can see, but on the different view it looks like a 3D. So the view is also very important, from which direction you are seeing the image, and that becomes the very challenge. So you might have seen that a lot of people who are good at drawing, they can draw 3D looking drawing by different using different cues of a human being. Similarly, the viewpoint difference is also very important. If the same car, if you see from a frontal, it will completely different. If you see from the back, it will look completely different. How do you know it is the same car or not? Or okay, all those questions we are want to ask, and whether it is the going frontal or it is going backwards. And now we are talking about autonomous driving. Again, we need to process such kind of a data. Scale is also very important. Scale, when I see what I mean here is that if you take some images from a very far off places or from a distance, it will look very smaller because of the perspective vision. When I say perspective vision, means like a human eye. We don't see parallel line as a parallel because of the perspective distortion or perspective projection, and that would change the scale aspect of the object. So if something which is taken from a closer camera would look little bigger, and something which is taken from a far off camera would look smaller. So same object would appear different shape and size from a different view position or view distance. That is another big problem in computer vision. How do you handle varying scales in the while designing your algorithms? And again, you can see that this particular image is showing how the dog class. If you see that here, there are multiple dogs. Okay, all are of same category as a dog class, but these actually dogs are completely different. They are no longer very similar to each other, but there is something which is common across all of the dog. So how do you really find out that common between the multiple instances and still do a better classification? That is another important problem in the computer vision. Occlusion is another very important problem. If you see this particular image, can you tell what is this animal name? It looks like a cat. Okay, so cat means, again, how do you know? Even so, our brain is capable of processing such an information with a partial information, but actually the computer science or computer vision algorithm are not very efficient that it can process the partial, because if you train with a full data and if you show a partial data, the algorithm may say that, okay, I don't know what you're talking about, and then I cannot classify into this thing. But humans are very good at all those things. We have evolved over multiple years, and then we have gained such a skill to overcome such a limitation. So this is again very important, how we can develop algorithm which can handle even occlusions. Why computer vision is very important today? Because we use computer vision for different application like safety application. If we have accident in a road, if we have a CCTV camera, we can record the accident, and then really if we can identify if accident happened automatically, then we can send the help to that particular location. And if you want to file a case or insurance money, you can also find who is the guilty for doing the accident, and then some actions can be taken. So safety is one of the important computer vision application. Healthcare, so people are using this computer vision or medical image processing for detecting the benign or malignant cancer in the, this is the breast image, mammogram image, where people are taking this mammogram to see whether any such calcification or some kind of a tissue formation is there, so that they can diagnose it early, and then some treatment can be given to the patient so that fatality rate can be reduced. People also using industrial automation for inspection of the ICs or objects in a different scenario. People also using robotics. Many students like to work in robotics. The intelligence in the robotics come from the vision side. We put the cameras into the robot, and then they see the things, and then they interpret the things, and then try to do tasks that's supposed to be like robo club is there, robo play is there, robo soccer is there. So many things are there. People also using entertainment, like now if you go to mall, you will see a lot of virtual reality or augmented reality gaming things are there, and we can use it for different entertainment applications as well. People also use it for retrieval. Let's say you might have used the Google image search, you upload an image and it will tell you the similar looking image for this thing. Moreover, now a lot of apps have been developed to process the QR code, and you can take the image of a scene, and then it will tell about search the particular product into the website, and then you can buy that thing immediately. So a lot of these are the some list of applications, but there are broad range of applications available in the area of computer vision. So what are the related field of computer vision? So robotics is the related field, human computer interaction, medical imaging, neuroscience, optics, computational photography, graphics, machine learning, image processing, recognition, deep learning, geometrical reasoning. All this actually are somehow related to computer vision. Sometimes we use computer vision in those things, and sometimes machine learning is used in computer vision, and all those aspects of that. So, some kind of interchangeable aspect of this interrelations is exist between the computer vision and other fields of engineering. So again, just to pose a very difficult problem to all of you, I think if you really want to start with an algorithm to design an algorithm, you can start with, that's a very simple problem. So can you count how many people are there? If you can count how many people are there using an algorithm, that means your algorithm are a perfect algorithm, and then you can process the computer vision problem, and then you can work on any other field of the computer. So this is a very simple problem. A human can do very easily by seeing the heads, but can you use the computer vision algorithm to really count the head? How do you really segment the head from the image, and then count how many are there, and then put a label there, and then you can tell that, okay, these are the numbers effectively. And it's very useful problem because you can do a crowd control, and then you can monitor the how crowd is changing and behaving, and all those aspects is also possible. So coming to little bit of correspondence between the biological vision and computer vision. If you see that computer vision is inspired from a biological vision, we have a human eye, left and right eye, which basically have a certain field of view. So you can see that there's some field of view is available for each of the eye. This is the left field of view, this is the right field of view, and then there is a common field of view. Common field means both right and left image can see that common region. And then there is optical lens, temporal retina, optic nerve, optic chiasm, LGN cells, and primary visual cortex. So the visual cortex, all the information gathered by this sensor, and then the visual cortex actually do interpretation what we are seeing, and what basically some kind of information can be given to the brain so that it can take a decision. So let's say when you drive a car or a bike, your brain is actually processing the visual information given by eyes, and then it is so fast that we don't really meet an accident. But imagine if you want autonomous driving, you will have a lot of accidents. But although now it is very successful, but still challenges are there. So a little bit of different between the computer vision and computer graphics. If you are from computer science background, you might have read about computer graphics. So in the computer vision, actually, what we deal with, you can say that computer graphics is the inverse of a computer vision. In graphics, we have a 3D model of the object, and we try to render as a 2D into the images. Okay, and then in general, what happened in the computer vision? What we do is we try to take image which is in two-dimensional, and then try to project into 3D information. So that is the basic difference. In graphics, we take the 3D scene, project into 2D, and then render onto the screen. In the vision, we take the images and then process the image and try to extract the 3D information. So it's kind of an inverse of a graphics is the vision, and most of the time techniques can be also interchanged. And when we talk about 3D, means we can talk about the objects, material, shape, geometry, motion, semantic, 3D pose, and so on and so forth. So this is a kind of a little inverse problem, and it becomes really hard because you have very little information, and then you have to project, extend the information which is of a higher dimension in nature. So there are computer vision is an in-post inverse problem, and many 3D scenes yield the same 2D images. So same 3D scene can give different 3D scenes can give you same 2D images, and how do you really recognize which is what and what is how to process those information. And there are additional constraints like knowledge about the world is also required when we really work in the from images to the real world information. So little bit again difference in the image processing and computer, where most of the students are undergraduate now learning image processing. So in image processing, what we deal with the handling the individual pixel level information. Let's say if you see that we are denoising it, or we are trying to plot the spectrum of the things, and we are trying to find the edges or the corners, or we want to remove the noise from the signal, let's say Gaussian noise, or we can take the scale space pyramid, so we can create the different scale space behavior of the images, or we can do the blending on operation, shape recognition from the stick kind of a model, and distortion removal. All those basically comes under the image processing aspect. And in general, image processing is the first task we do before computer vision, because once the pixels are cleaned, and then we can actually use for different interpretation operation. Although now the boundaries between computer vision and image processing is very narrowed down, because many of the image processing algorithm are actually now very sophisticated. You can call them to be a computer vision pipeline as well. So just to tell you about the one computer vision machine learning difference. So computer vision basically deals with the image classification, and if you see this particular ImageNet challenge data, if you search ImageNet challenge data in the internet, you will find that there are millions of images has been given by the what you say the researcher to develop your algorithm to classify them into different categories. If you see that there are fruits, objects, locations, bird, aeroplane, car, and then you have to categorize into one such category. There are 1,000 such classes are there, and we need to develop both feature extraction algorithm as well as the machine learning algorithm. So machine learning would do the classification task, computer vision would do the feature extraction part, and when you combine these two, it will do a actual classification task. So over the year, due to the deep learning, emergence of deep learning, if you see that the accuracies has been improved significantly and error has been reduced significantly. In the 2010, where we were not using any such machine learning or deep learning algorithm, the errors were around 28%. And if you see that 2016 2017, this has reduced to 2% or something, just because of the introduction of the deep learning architecture. So this is the very effective result. It shows that how the image classification on image data set has been improved due to the presence of new deep learning algorithms. And similarly, you can see that number of publications is increasing exponentially. Okay, in the CVPR, and if you see that the submission versus accepted, so the blue ones are the submission, and green ones are the accepted papers. And CVPR is the one of the very top conference in the computer vision society. And if you see that the number of accepted paper is way too low than the submitted paper because it's a highly competitive field. Lot of people, companies are working in this area. If you work in this area, you have very high chances of getting good job in some company. Although you have to be very good at that because unless you are good, people would not hire you. So you have to understand what you are doing and then have a better hold of the subject. So this is the very basic about the computer vision. Now a little bit go into a little more detail. If you see another very simple example, if you see this particular image, it looks like a 3D globe from one particular view. But if you see from a different view, it is looking like just a normal lawn. And but when you see from a different view, it looks like a 3D. So it's kind of a how you design something which is look like a it can fool the human vision and then it look like a 3D. So little bit coming to the image formation aspect. So how image formation happens. So I will not talk about the projective geometry and projection matrix. I will just basically talk about the pinhole camera. So what do we really need to basically make an image? So what we talk about the image formation. So what happened in general, we have photographic film. So I don't know whether you have seen any photographic film because young generation always see the digital camera. Earlier, we used to have a photographic film, and the objects would emit or reflect the light from different points, and then we will use this photographic film to record this image. But what you see here, multiple points, so this light is coming hitting here and then it is being reflected to all possible direction. It is going here, 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 and from this point also it is going here and there. So once you form such kind of an image, it will look like a very blurry image and it will have no such information because all the multiple points are getting projected into same location. So it's kind of a many to one mapping, and it will we have no such distinction between the different points of the real world into the photographic film. So this is not a very good model to really capture the images. So we don't get a good image due to the such geometrical setup. So what we do is basically we put a barrier. Okay, so what we will do, we will only allow one light to pass through. Only one ray can pass. So we put a barrier here. Barrier means some kind of obstruction to the light. Okay, and then only put a small hole here. Okay, one single hole. That's called the pinhole. Pinhole means only we can say that only one ray of the light can pass through that particular hole. So now what happens? This particular point would image at here. This particular would image would here, and every possible point would only image at one particular location in the photographic film, and then we should be able to image it. So that's called the pinhole camera setup, and this opening is typically known as the aperture. Aperture is the another word. If you're familiar with the photographic terminology, we call it to be an aperture. So this is a very simple setup. So we have a real object. This real object, from every possible point, rays would be going through this pinhole, and then this is the image plane, and we will see that image will be forming upside down at the distance focal length f from the center of the projection, and this is called the center of camera. This is called the image plane, and image plane generally kept f distance from the center of the camera, and this is the real world object. And if you create a virtual image, if you see that, okay, if you bring this image plane here, you can see that the image would be no longer would be inverted, because after the center of projection it is going to upside down. But if you take the image beforehand coming here, then it will be a same image. So that's kind of a geometrical ideas we can use in designing our camera or lens setup. So this is the very first, image formation happened in the China and Greece. They have made this first pinhole camera that is called the camera obscura, and it has been done in 470 BC and 390 BC. So it's very old magic. So people are clever enough to find out how to create images. And this is again, you can see in your house also, you can see some pinhole camera setup. These are all, pinhole. Suppose a very small tiny hole is there in your window, you will see some kind of a image formation. This is another, lot of small tiny bushes are there that will give a image kind of a setup. This is again a camera obscura. Okay, this is again a pinhole camera setup. So when you use basically this camera idea, you have a problem like, how do you know that how tall this woman is, how high is the camera, what is the camera rotation, what is the focal length of camera, and which ball is close. So all this question need to be answered when we really work with a computer vision problem, and then we have to really use only the single image and then reason about what would be the physical parameters of the object. Okay, although all those things will be difficult to cover in all this particular class, but we need to use the geometrical concept, let's say focal length, the distance of the camera from the image plane, and the camera calibration matrix, and all those things are required to really talk about all those things. So typically in pinhole camera, people also use some kind of a lenses. So lenses is again to basically collect the beam into one particular direction. That is another lot of research is going on how to build a proper lens, because if you want to collect a lot of light into one such point, you can use the lens which will take the beam of the light and then focus into only a single point. So real world, we have a 3D world, and then you take the image, it is 2D, so we lose one dimension, and due to this loss of one dimension, we become unaware how to solve this problem, because we don't know the depth of the object, and then how do we really talk about the depth estimation from the images. So that's again a bigger problem for us. Okay. So basically again we need to talk about so this is called the projective geometry. Projective geometry means you can see that the parallel lines are looking like converging. Okay, so like if you see here in the previous setup, the lines are in converging into one such point, and then basically we can say that all the lines which is going parallel would meet at some point in the infinity, and that becomes the perspective projection. So perspective projection means we will see that the light is bending and then meeting at some particular point, and that becomes the kind of a perspective projection, and then it kind of it shrink the shape. So if you see that this particular candle is basically very small, if you put the image plane here, where my arrow is, this would be very small image. But if you take this focal length or image plane too farther, the image will be little bigger. So this is called the perspective foreshortening due to the perspective vision concept. Okay, so that is the idea. This is basically the idea. So we can say that in the perspective geometry or the perspective vision, length and area is not preserved, and everything else is preserved. So basically line would remain the line, parallel lines would become the parallel line, but length and area are not preserved. So if you see that there are A, B, C, D, A, B, C, these are the different objects, and if you use the perspective vision, you can see that A, B is mapping to B prime, C is mapping to C prime, A is mapping to A prime, and this is all kept at different distance from the origin. This is the origin. So this is called a perspective position, which is causing the perspective foreshortening of the different object due to its closeness or the nearness or the farness from the center of projection. So what you see here, that another thing is, although this in real world these are the parallel lines, but here it will look like a converging. Okay, so it's kind of it looks like it is meeting at point. So that is called the perspective or projective geometry. So we lost the length and the angles, but line is remaining line, and the parallel lines would remain the parallel sometimes. Okay, so straight lines are still straight line. Okay, that is preserved. So if you see that thing, in the perspective projection, we will lose this parallelity of the lines. It will meeting at some kind of a point. So this is no longer parallel. So in the projective geometry, we will lose the parallelness of the object. But if it is a orthographic projection, then we will have a preserve the parallel lines also. Okay. So this is the point where all these parallel lines are meeting, is typically known as the vanishing point. And if you see that thing, there are multiple parallel lines would map to different vanishing points. So there are infinitely many possible vanishing points are possible. And if you imagine all possible lines in the two-dimensional plane would meet at the one such point, and all those points form a line which is called the vanishing line. So I hope it is clear. This is one parallel line meeting it here. This is another parallel line meeting here. If you draw so many parallel lines, will form a multiple points, and all those points also form a line. That is called the vanishing line. So we call vanishing points where in the projective geometry or perspective projection, the parallel lines would meet at a one point, and similarly, there is a vanishing line. All the points which lie on the all the vanishing point which lie on a single line is called the vanishing line. So this is the kind of an idea. So if you see this thing basically, these are the one such parallel line which is meeting here. This is a parallel line which is not meeting. It is meeting at the infinity. So this particular line, we can show that it is meeting at the infinity. Okay, and this is another vanishing point. So there are many possible directions we can have the vanishing point. And this is another example. You can see that this is very clear from this image. It looks like these lines are converging in one particular points. Okay. So coming to challenges in application of the computer vision. So the challenges are the humans see this, but actually computers see this. So this is kind of very perception is very hard for us, and we have 3D scene is mapped to 2D image. So again, that is a very difficult problem for us. I'm not going to play this video, but I will see if I can play this video. I think. Let's see. So this video actually shows that how I think you can go through this. Very fancy videos are there. I hope it will work here. 1 second. So these are some kind of illusion. This is the video I wanted to show you. So if you see this particular image, so this looks like it is going up. Okay, it is going up. It looks like it is going up from one particular view. Again, it is going. So it is actually not correct. Things cannot go from lower to higher height. But if you see from a different view, you will see that it is no longer a straight thing, but it is made in a manner that when we see from there, it looks like a going up, but actually it is going down only. So the view is also very important. How do you really? So this is called illusion. Okay. So visual, whatever you see may not be true most of the time also. So we say that seeing is believing is no longer valid now. Okay. That is also the perspective illusion. That is a perspective illusion. How do you see and then what do you interpret is completely different. Okay. So there are challenges like viewpoint orientation. So this is the same object, but you can see from 3 different view. And can you say that it is the same object or not? How do you really do a classification on image which is invariant to viewpoint variation? Occlusion or illumination is another important. So this is the same scene. 3 different illumination would lead to a 3 different scene of a same application. And can we say that this is the same object or not? That is the question we are asking. Again, motion is another important aspect. So if you see this bird, you don't see any face because the bird's head is moving so fast, and the frame that we capture in the camera, and it becomes a very blurry thing. And then how do you really deal such kind of a high motion thing? And again, this is another very interesting illusion. If you see that you perceive a triangle here, okay, Do you perceive a triangle here? But actually there is no triangle. But we perceive as if there is a triangle. Similarly, we perceive the sphere where the spheres are coming out. And then this particular image look like something is going inside and coming out of this thing. Similarly, here we also feel like a shape. And here it is very difficult problem. You can see that it appears as if dog is standing there. Okay, some people may observe dog, some people may not. But if you see closely, you will look like some dog is there. So how do you really, humans are very capable of finding such a unexisting thing. That is also very interesting. And computer vision has to deal with such kind of a scenario as well. And then intra-class variabilities, the same chair class can have multiple such shapes, and then still they are chair class only. Okay, how to deal with such a intra-class variation? And this is another very interesting M's rooms illusion. If you find time in YouTube, actually, people actually create. I will show you in the YouTube only. I think that's. So if you see this particular image, I think you can listen also this thing. So you understood what is this Ames room illusion. So basically, that is again what we see may not be always true. So I think our brain can be also fooled, and that is kind of a really when we deal with computer vision kind of a problem, we have to be careful with such kind of scenarios. Uh, I will go through the applications of computer vision and conclude my talk. So people are actually using in optical character recognition. So digital recognition is one of the important application. You can use it for translation, live translation. Now our handwritten recognition. So if you write with through a pen or something, it will convert into numbers, and then it can go into the text box immediately. So a lot of techniques have been developed, which is typically known as the OCR, and which is still a important area to be work on because a lot of languages are there. Hindi character, English character, Malayalam character. How do you really recognize using the existing algorithm? That is the challenge. People also using face detection. Let's say most of you using the Facebook or mobile phone to detect face, or smile detection also is possible. So I think a lot of Snapchat, if you use, they have a lot of face filter which can make a lot of things in the face. So that kind of a very fancy applications are there. People are using a computer vision for this thing. People also using for shape recognition in Snapchat. They convert into one face to different face. There is also camera that basically developed to detect the smile, and it will capture the only aesthetically pleasing images, and do not capture which is not so aesthetically pleasing images. That is another good application. People also use an object recognition in supermarket, like Amazon has come up with a market where a lot of computer vision cameras has been used, and then you don't have to really go with a any person is not there. You go walk in there, lift these things you want, automatically your transaction credit card will be charged for the objects that you choose, and then you can go out of the room without any disturbance. So there is no such cashier in the mall. You go with a registered user, go into inside that thing, and then as soon as you pick the things, automatically billing everything happens, and then you go out of the room without any problem. So these are the cameras they are using, and then they are using this camera to scan the object, and then also counting how many you have taken. People also using biometrics, a forensic application. Like most of you have the Aadhaar card, you have given the your iris image, fingerprint image, and face image, and people are using to recognize whenever you claim that you are such a such person. The algorithm recognize you whether you are trailing truth or not. Okay, so this is one of the very interesting case where this girl has been identified by her iris pattern after such a long year. This is the real story actually. People also using for facial login without an password, so you can use the facial login and then log in into your machines. That is also possible. And now there are algorithms which can also detect whether it's a fake image or it's a real image. So if you put a picture of your face, it will say it's not a real face, and then it will not open the password. So that is also being taken care by the algorithms now. Now people even developing some techniques to create 3D structure. Uh, these are the you can actually create a 3D model out of this laser scan device. And people also use the Google Lens. Many of you use Google Lens. It can tell you the location and all the other information. People also use for 3D information from the images. So you take multiple such images and then create a 3D structure from the images. That is called the 3D structure from motion. And this is very interesting paper if you want to know more about it. Building Rome in a day. They have used multiple such images and then created a Colosseum in a very short time. People also using for human shape capture. So you use multiple IR camera and then create a 3D model, of digital model of the human, and then you can texture it, color it, and then you can print it into a 3D printer, and then it is also very possible using computer vision applications. So this is the 3D printed statue of an Obama, where images were taken from a IR camera, and then 3D structure from motion has been done to create the face, which is very look real to the actual face. People also usually, so suppose if you like animation movies, lot of transfer of animation from one object to the cartoon object is happening due to the lot of computer vision calibration aspects are there, and this is the real character, and then this is on a screen you will look like this. So they are using this IR sensor, and the motion of the body has been transferred into this graphical character in the virtual world. These are some of the good videos you can actually watch. I will share the slides with the madam, and then you can watch this video how people are using computer vision and 3D lidar scan or laser scan or IR based scanner for converting into different entertainment applications. So 3D robot, all those things are there. Object recognition. These are the good videos I think one can see and understand different aspect of this thing. People also using in sports. People are like you might have seen that trajectory of the ball they show in the IPL. Even in the football they show that whether you are offside or not, or whether any mistake has been happened in the tennis or badminton. They also use all this computer aspect to really showing the virtual world on images, and then it looks like very real. Nowadays even they show 3D, pseudo 3D kind of a view in a two dimensional, so it will look like a they use something called you know time of flight camera, and they capture the little distance information, and then basically it looks like very real, that as if we are actually standing in a stadium and seeing the real game. People also using medical imaging for image guided surgery, 3D imaging, MRI, CT analysis. That is another very important application of computer vision and graphics at large. Auto cars, Uber, has. So this is the Carnegie Mellon University has developed this Uber autonomous driving, and that has been bought by the Uber to do a lot of research in that area. So again, we can also work in such area using computers. These are the sensors you can see, lidar, camera sensors, and they are using to detect any pedestrian there or not. These are the different sensors they are using: lidar, radar, multiple cameras. These are the stereo cameras. So many things they are using actually, and different directions actually, all possible directions they take. This is another Google Street View, another very interesting application. Industrial robot people are using for robotic manufacturing, inspection, alignment, docking kind of an application. That is another very good application of the vision guided robots for positioning nut runners on a wheel. People also using in space, 3D extraction from the space data. Rover is going into the traveling in the Mars and Moon. They are supposed to travel on their own, so they take the images from the scene and then reconstruct the 3D and then try to do certain tasks. So people are using, let's say, panorama stretching, 3D terrain modeling, obstacle detection, position tracking. And I think if you want to know more, actually, you can read this article, Computer Vision on Mars, that will talk more about the things that US is doing on Mars to make robot intelligent and navigate in the particular location. You can also go through the 2019 Changi 4 Moon Lander Challenge. So how does they do vision assisted landing has been achieved by the algorithms, and then no, there is no control. It's autonomous way of landing into a particular site. And ISRO is also working on same concept, how to design our own lander based on the vision based lander or radar based lander, all possible sensor we can, so that we can do a safe landing. Because once we do a safe landing, we can navigate and then do a lot of. Otherwise, the speed is so fast that it will, if it hits to the surface, we will damage all the equipment, and there's no use of the mission. People also using mobile robotics, RoboCup, and other thing as well. People are using different applications. I think a lot of kids from your college must be doing such kind of a work as well. And this is the augmented reality, which is the final slide. I want to show that now HoloLens has been come where you can actually both the virtual world and real world can be superimposed on the screen, and then you can see the different aspect. So these are the some of the challenges, and these are the companies which are working in the computer vision area in across the world. And I hope many of you would find job in some of these companies and then work in this area. So with this, I will conclude my talk. If you have any question, I will be very happy to answer. Thank you.
Good evening, sir.
Yeah, good evening.
Sir, can you talk about the disadvantages with computer vision, like the privacy issues that arise?
Yeah. So privacy issues are there, but again, you need to develop techniques to handle those privacy issues. Let's say face is something people don't want to, reveal their identities. So what they do is basically they find out the face and then blur the face on the using some non-linear transformation, so that you can protect the identity of a person. So you need to use the technique itself, computer technique itself, to protect the people from a identity theft and other things. Yes, but yeah, there are disadvantages of computer vision. Once you take a face images or once you lose this data, people may misuse it. So you have to be careful. But again, we have to use the technology only to solve the problem. So I think computer vision can definitely help in that. So manually doing the occlusion of the face or changing the face position or the blurring the pixels there may be difficult. So you have to develop algorithm which is good enough to do certain tasks.
Thank you, sir.
Thank you. Any other question?
All students are requested to fill the feedback form provided in the chat box. Certificates will only be provided to the ones who have submitted the feedback form. So please make sure that you fill it without any fail. So it's time to officially wind up the session. On behalf of IEEE SB SNGCE, let me thank Dr. Deepak Mishra, Professor and HOD, Department of Avionics, Indian Institute of Space Science and Technology, for his valuable time and for the wonderful presentation that was very informative. Thank you so much, sir.
Thank you. Thank you very much for kind invitation and good luck to all of you. Bye bye.
Thank you, sir. Next, let me thank Professor Pratibha Varghese, Branch Counselor, IEEE SB SNGC, for her wholehearted support and guidance. I would also like to thank all the IEEE SNGC members for their active participation. Thank you all.
Dear students, you can leave the session only after filling the feedback form. The certificates will be provided only to those who have filled the feedback form. Thank you. Deepak sir.